Hello everyone. In previous class we discussed about what is the differentiator amplifier, integrator amplifier, log and anti-log operational amplifier. पिछले वाली क्लास में हमने देखा था इंटीग्रेटर एम्पलीफायर कैसे काम करता है, उसका सर्किट डायग्राम, डिफरेंशियल एम्पलीफायर, और हमने स्टडी किया था लॉग एंड एंटी लॉग ऑपरेशनल एम्पलीफायर सर्किट. So now today we will study about what is the voltage to current converter and current to voltage converter. After this we will move the next topic, name is comparators, operational amplifier, and next is a Schmitt trigger circuit by using operational amplifier circuit, and finally the references of this presentation. So in this lecture we cover all these topics one by one. Let's start with topic 1, voltage to current and current to voltage converters. Voltage and current are the basic electrical quantities, and they can be converted into one another depending on the requirements. The voltage to current converter and current to voltage converter are the two circuits that help in such conversion, and these are also the linear application of the operational amplifier. तो अभी आपने जो पढ़ा हुआ है वोल्टेज टू करंट एंड करंट टू वोल्टेज कन्वर्टर सर्किट इलेक्ट्रॉनिक्स में पढ़ा होगा आप लोगों ने. अब जो हम बनाएंगे वो ऑपरेशनल एम्पलीफायर के थ्रू हम वोल्टेज टू करंट एंड करंट टू वोल्टेज कन्वर्ट करेंगे. सो दिस इज द सर्किट डायग्राम फॉर द वोल्टेज टू करंट कन्वर्टर. A voltage to current converter or V2I converter is an electronic circuit that takes current as the input and produce the voltage as the output. तो आउटपुट में हमें जो मिलता है उसको हम पहले लिखते हैं. तो वोल्टेज टू करंट मींस आउटपुट में वोल्टेज मिलेगा और इनपुट में हम उसको करंट देंगे. This section discuss about the operational amplifier based voltage to current converter. An operational amplifier, in short op amps, based voltage to current converter produce an output current when a voltage is applied to its non-inverting terminal. The circuit diagrams of an operational amplifier based voltage to current converter are shown in a figure. So this is the circuit diagram for voltage to current converter. In the circuit shown above, an input voltage Vi is applied at the non-inverting input terminal of the operational amplifier. We can know that कि जो operational amplifier होता है उसमें एक inverting terminal होता है और दूसरा non-inverting terminal होता है. Inverting terminal को हम माइनस साइन से रिप्रेजेंट करते हैं और non-inverting terminal को हम पॉजिटिव साइन से रिप्रेजेंट करते हैं. So the input voltage Vi is applied to non-inverting input terminal of the operational amplifier. According to the virtual short concept, the voltage at the inverting input terminal of an operational amplifier will be equal to the voltage at its non-inverting input terminal. So, the voltage at inverting input terminal of the operational amplifier will be Vi. The nodal equations at inverting input terminals node is Vi upon R1 minus of I0 is equal to 0. So we can find the value of I0. So I0 is equal to Vt divided by R1. Thus the output current I0 of a voltage to current converter is the ratio of its input voltage Vi and the resistance R1. ये हम सर्किट डायग्राम में अभी हमने जो इक्वेशन निकाली है आई नॉट की, उसी को हमने लिखा हुआ है कि जो आई नॉट है वो रेशियो है Vt का और रेजिस्टेंस R1 का. So we can rewrite the above equation as I naught divided by V1 is equal to 1 upon R1. The above equation represent the ratio of output current I naught and the input voltage Vi, and it is equal to the reciprocal of resistance R1. The ratio of the output current I naught and the input voltage Vi is called as transconductance. तो ट्रांसकंडक्टेंस क्या होता है? द रेशियो ऑफ आउटपुट करंट आई नॉट एंड द इनपुट वोल्टेज वी आई. वी नो दैट द रेशियो ऑफ आउटपुट एंड द इनपुट ऑफ द सर्किट इज कॉल्ड एज गेन. सो द गेन ऑफ एन voltage to current converter is the transconductance, and it is equal to the reciprocal of the resistance R1. So this is all about the voltage to current converter. Next is a current to voltage converter. A current to voltage converter or I to V converter is an electronic circuit that takes current as input and produces the voltage as the output. This section discusses about the operational amplifier based on current to voltage converter. An operational amplifier based current to voltage converter produced an output voltage when the current is applied to its inverting terminal. उसमें हमने क्या किया था? नॉन इन्वर्टिंग टर्मिनल में इनपुट दिया था, इसमें हम इन्वर्टिंग टर्मिनल में इनपुट देंगे. द सर्किट डायग्राम ऑफ एन ऑपरेशनल एम्पलीफायर बेस्ड करंट टू वोल्टेज कन्वर्टर इज शोन इन अ फिगर. सो दिस इज द सर्किट डायग्राम फॉर करंट टू वोल्टेज कन्वर्टर. In the circuit shown above, the non-inverting input terminal of the operational amplifier is connected to ground. That means 0 volt is applied at its non-inverting input terminals. According to the virtual short concept, the voltage at the inverting input terminal of the operational amplifier will be equal to the voltage at its non-inverting input terminals. So, the voltage at the inverting input terminal of the operational amplifier will be 0 volt. The nodal equation at the inverting terminals node is minus of I1 plus 0 minus of V0 divided by RF is equal to 0. So we can find out the value of I1. Minus of I1 is equal to, or minus of II is equal to V0 divided by RF. And the output voltage V0 is equal to minus of RT into II. Thus, the output voltage V0 of current to voltage converter is the negative or product of the feedback resistances RF and the input current. It observed that the output voltage V0 is having a negative sign, which indicates that there exists a 180-degree phase difference between the input current and the output voltage. So we can rewrite the above equation as V0 by II is equal to minus of RF. The above equation represents the ratio of output voltage V0 and the input current II, and it is equal to the negative of feedback resistance RF. The ratio of output voltage V0 and the input current II is called as trans resistance. So we know that the ratio of output and input of the circuit is called as a gain. So the gain of the current to voltage converter is its trans resistance, and it is equal to the negative feedback resistance RF. So this is current to voltage converter. Next topic is comparators. The operational amplifier comparators compare one analog voltage labels with another analog voltage label or some preset reference voltage V reference and produce an output signal based on this voltage comparison. In other words, the operational amplifier voltage comparator compare the magnitude of the two voltage input and determine which is the largest of the two. तो कंपैरेटर नाम से समझ में आ रहा है, दो सिग्नल को कंपेयर करना है और कंपैरिजन करने के लिए हम कंपैरेटर सर्किट का यूज करते हैं. Now next is the operational amplifier comparator circuit. So this is the circuit diagram for the comparator. If Vn is greater than to V reference means input voltage जो हमारा reference voltage से ज़्यादा है, then the output voltage is equal to plus Vcc. If input voltage Vn is less than to V reference, then the output voltage is equal to minus Vcc. ये इसका ग्राफ बना हुआ है दोनों कंडीशन के लिए. आप ग्राफ में देख सकते हैं नेगेटिव और पॉजिटिव दोनों आपको दिख रहा है प्लस Vcc एंड माइनस Vcc. पहला रीजन जब Vn हमारा Vn मतलब इनपुट वोल्टेज, जब इनपुट वोल्टेज हमारा लेस देन है रेफरेंस वोल्टेज से तो हमारा Vcc जो हमें नेगेटिव मिलेगा, आप यहाँ पे भी देख सकते हैं. और जब हमारा Vn ग्रेटर देन है V रेफरेंस से तो हमें प्लस Vcc मिलेगा. सो दिस इज द फर्स्ट पोर्शन. Consider the basic operational amplifier voltage comparator circuit. ये एक voltage comparator circuit हमने लिया हुआ है. रेफरेंस वोल्टेज से हम इनपुट वोल्टेज को कंपेयर करते हैं और फिर हमने एक ग्राफ को बनाया है. With reference to the operational amplifier comparator circuit above, let's first assume the Vn is less than the DC voltage label at V reference. अभी हमने पढ़ लिया Vn is less than to V reference. As the non-inverting positive input of the comparator is less than the inverting or negative input, the output will be low and at the negative supply voltage minus Vcc, resulting in a negative saturation of the output. If we now increase the input voltage Vn so that its value is greater than the reference voltage V reference on the inverting inputs, the output voltage rapidly switches high towards the positive supply voltage plus Vcc, resulting in positive saturation of the output. If we reduce again the input voltage Vn so that it is slightly less than the reference voltage, the operational amplifier's output switch back to the negative saturation voltage, acting as a threshold detector. Then we can see that the operational amplifier voltage comparator is a device whose output is dependent on the value of the input voltage with respect to some DC voltage label. As the output is high when the voltage on the non-inverting input is greater than to the voltage on the inverting input, and low when the non-inverting input is less than the inverting input voltage. This condition is true regardless of whether the input signal is connected to the inverting or non-inverting input of the comparators. तो इनपुट जो हम लगा रहे हैं वो हमने चाहे नॉन इन्वर्टिंग टर्मिनल में लगाएं चाहे इन्वर्टिंग टर्मिनल में लगाएं, वो क्या करता है, कंपेयर करता है एक डीसी रेफरेंस वोल्टेज से और हमारी वैल्यू हमें हाई और लो देता है। We can also see that the value of the output voltage is completely dependent on the operational amplifier power supply voltage. In theory, due to the operational amplifier high open loop gain, the magnitude of its output voltage could be infinite in both the direction. However, practically and for obvious reason, it is limited by the operational amplifier supply rail giving Vout is equal to plus VCC or Vout is equal to minus VCC. We said before that the basic operational amplifier comparators produce a positive or negative voltage output by comparing it voltage against some, compare its input voltage against some preset DC reference voltage. Generally, a resistive voltage divider is used to set the input reference voltage of a comparator, but a battery source, Zener diode or potentiometer for a variable reference voltage can also be used. Next is a comparator reference voltage. So in theory, the comparator reference voltage can be set to be anywhere between the 0 volt and the supply voltage, but there are practically limitations on the actual voltage range depending on the operational amplifier comparator being device used. So the case number 1, V reference is equal to R2 divided by R1 plus R2 into VCC. In case 2, V reference is equal to V into RB divided by V into RA plus V into RB into VCC. Case 3, when the DC battery has a reference source, so V reference is equal to V battery, means reference voltage is equal to battery voltage. And if we use the Zener diode for the reference source, so V reference is equal to VZ, means Zener voltage. तो ये 4 केस है हमारे पास. जब हम फिक्स वोल्टेज डिवाइडर यूज करेंगे तब रेफरेंस वोल्टेज क्या होगा, जब वेरिएबल पोजीशन रेफरेंस यूज करेंगे तब रेफरेंस सोर्स हमारा क्या होगा, और डीसी बैटरी जब यूज करेंगे तब रेफरेंस सोर्स की वैल्यू क्या होगी, और जेनर डायोड जब यूज करेंगे तब रेफरेंस सोर्स हमारा क्या होगा. ये चारों डायग्राम में हम देख सकते हैं. नेक्स्ट इज अ पॉजिटिव एंड नेगेटिव वोल्टेज कंपैरेटर. So a basic operational amplifier comparator circuit can be used to detect either a positive or negative going input voltage depending upon which inputs of the operational amplifier we conduct the fixed reference voltage source and the input voltage to. In the example above, we have used the inverting input to set the reference voltage with the input voltage connected to the non-inverting input. But equally, we could connect the input of the comparators the other way around, inverting the output signals of shown above. Then an operational amplifier comparators can be configured to operate in what is called the inverting or non-inverting configuration. So first one is called the positive voltage comparators. This is the circuit diagram for positive voltage comparator circuit. The basic configurations for the positive voltage comparators, also known as a non-inverting comparator circuit, detects when the input signal Vin is above or more positive than the reference voltage. पॉजिटिव वोल्टेज कंपैरेटर कब कहलाएगा, जब हमारा जो इनपुट सिग्नल है वो ज्यादा है ना, रेफरेंस सिग्नल से. सो द आउटपुट एट वी आउट एंड विच इज हाई एज शोन इन फिगर. नॉन इन्वर्टिंग कंपैरेटर सर्किट, जो कि हमारा पॉजिटिव वोल्टेज कंपैरेटर सर्किट के अंदर आता है. In this non-inverting configurations, the reference voltage is connected to the inverting inputs of the operational amplifier with the input signal connected to the non-inverting input. To keep things simple, we have assumed that the two resistors forming the potential divider network are equal and R1 is equal to R2 is equal to R. This will produce a fixed reference voltage which is one half that of the supply voltage, and that is VCC by 2. While the input voltage is variables from 0 to the supply voltage. When Vn is greater than to the V reference, then the operational amplifier comparator's output will saturate towards the positive supply rail VCC. When Vn is less than to the V reference, so the operational amplifier comparator output will be changed state and saturate at the negative supply rail or 0 volt as shown in the figure. Next is the negative voltage comparators. The basic configuration for the negative voltage comparators, also known as the inverting comparator circuit, detecting when the input signal Vn is below or more negative than the reference voltage V reference, producing an output at V out which is high as shown in figure. तो इसके अंदर हम पढ़ेंगे inverting comparator circuit जो कि negative voltage comparators में आता है. In an inverting configurations, which is the opposite of the positive configuration above, the reference voltage is connected to the non-inverting inputs of the operational amplifier while the input signal is connected to the inverting input. Then when Vn is less than reference voltage, the operational amplifier comparators output will saturate towards the positive supply rail VCC. Likewise, the reverse is true. When Vn is greater than V reference, the operational amplifier comparator's output will change state and saturate towards the negative supply rail 0 volt. This is shown in a figure. Now then, depending upon which operational amplifier input we use for the signal and the reference voltage, we can produce an inverting or non-inverting output. We can take this idea for detecting either a negative or the positive going signal one step further by combining the two operational amplifier comparator circuit above to produce a window comparator circuit. So this is regarding positive and negative comparator circuit. The next topic is Schmitt trigger. So first question is that what is a Schmitt trigger? Schmitt trigger is a comparator, not exclusively, circuit that makes use of positive feedback or small change in the input leads to the large change in the output in the same phases. To implement hysteresis, a fancy word for delaying action, and is used to remove noise from an analog signal while converting into the digital signal. Schmitt trigger का सिंपल सा काम होता है नॉइस को रिमूव करना. नॉइस को रिमूव कब करना होता है? जब हम एनालॉग सिग्नल को कन्वर्ट करते हैं डिजिटल सिग्नल में. उस कंडीशन में नॉइस आती है सर्किट में, उसको रिमूव करने के लिए हम Schmitt trigger का यूज करते हैं. So this is the circuit diagram for Schmitt trigger. And second is a inverting and non-inverting Schmitt triggers using an LM193. It was invented back in 1937 by Otto H. Schmitt, whose legacy is somewhat understood, who called it is a harmonic trigger. Why Schmitt triggers are used? So comparators by nature are very fast since they lack the compensating capacitor found in their operational amplifier quotient. Comparators are not limited by the output slew rate and transition time are in the order of nanosecond. Comparators also have spatially sensitive input because of their very high gain. Even tiny change in the input can cause instant change of the state of the output. These problems get worse when the differential input signal reaches the dead zone. That is, the minimum input differential voltage required to maintain a stable output. Within this narrow range, the comparator has no idea what to do with its output. So which leads to some things called motor coding, which is the output oscillating. This problem also occurs with the signals that have a slow transition time. The input signal spanned enough time in the dead zone with reference to the reference voltage, of course, to create multiple output transition as shown in a figure. So this is the multiple output transitions without hysteresis. Blue line is the input and yellow line is the output. So this is the input. Blue line आप देख पा रहे हैं ये input है हमारा और ये जो yellow line आप देख पा रहे हैं दोनों के दोनों हमारे जो है वो output है. If you notice carefully, the input signal varies with the output swings and there's a lot of noise on the supply relay, which is a result of poor decoupling. If there was any logic connected to the output, it would detect the multiple transition and cause flip-flop would toggle multiple times, maybe causing something important to reset. This is something that can be remediated using hysteresis. In this case, with the additions of a single resistor between the inverting terminals and the output, the difference is marked again from the figure. So this is the figure for clean transition using hysteresis. Hysteresis का यूज हम जैसे ही करेंगे तो हमें यहाँ पे जो हमारा जो आउटपुट है वो हमें ज़्यादा क्लीन मिलेगा और क्लियर मिलेगा. Again note unstable reference voltage. Next, how does a Schmitt trigger work? A Schmitt trigger makes use of positive feedback. It takes a sample of the output and feed it back into the input so as to reinforce. So the peak of the output, which is the exact opposite to negative feedback, which try to nullify any change of the output. This reinforcing property is useful. It makes the comparator decide the state of the output it wants and make it stay there even within what would normally be the dead zone. Consider a simple circuit. So this is a circuit for inverting comparator with hysteresis. Assume the input voltage is lower than the reference voltage at the non-inverting pin and the output of therefore high. V star is the reference input voltage which creates a fixed bias at the non-inverting input. Since the output is high through the pull-up resistor, this creates a current path through the feedback resistor and slightly increase the reference voltage. When the input goes above the reference voltage, then the output goes low. Normally, this shouldn't affect a reference voltage in any way. But since there's a feedback resistors, the reference voltage drops slightly below the normal value because of the feedback, and the lower reference resistor are now in parallel with respect to the ground. Since the reference voltage is lowered and there is no change of a small change in input causing multiple transition, in other words, there is no longer a dead zone. To cause the output to go high, the input must now cross the new lower threshold. Once crossed, the output goes high and the circuit is reset to the initial configurations. The input has to cross the threshold just once, resulting in a single clean transition. The circuit now has two effective threshold or states. It is bistable. This can be summarized in the form of a graph. So this is the hysteresis curve और hysteresis loop, क्योंकि जिस पॉइंट से स्टार्ट हो रहा है उसी पॉइंट पे जाके एंड हो रहा है, तो इसको हम hysteresis loop बोलेंगे. This can be understood in the usual sense. The x-axis is the input and the y-axis is the output. Tracing a line from x to y, we find that once the lower threshold has been crossed, the hysteresis goes high and vice versa. The operation of non-inverting comparator is similar. The output again change the configuration of the resistor network to change the threshold to prevent unwanted oscillations or noise. Now next is the application of Schmitt trigger. Schmitt trigger find a wide range of uses, mostly as logic inputs. Again, it's not a nice thing to have a single logic threshold. In case of noisy or slow signals, multiple output transition may be result. Reading the datasheet of any logic chip, you will find that two thresholds are specified, one for rising edge and one for falling edge. This is evidence of Schmitt input action. Sometimes the logical gates are drawn with a little lightning symbols inside them. This is a styled hysteresis curve indicating that the device has a Schmitt trigger input. Finally, the conclusion. So Schmitt trigger are the useful when noisy signals are involved, and they clean up the noise and prevent unwanted multiple transition and oscillation. So this is all about the Schmitt trigger circuit. Now next is the references of this presentation. So these are the references. And thank you for watching this video.